Thank you for joining. Thank you, everyone. So we start our lecture today. We have a guest from Eindhoven, Professor Cristina Nan. I'm going to introduce her briefly, and we're gonna hear her lecture, and then hopefully we will have some time for Q&A and discussion. So thank you so much for joining us. Cristina Nan has been an assistant professor at TU Eindhoven's ADE chair since 2020. Cristina previously worked as an assistant professor in design and digital fabrication at the University of Edinburgh School of Architecture and Landscape Architecture from January 2016 to 2022, as well as the international director of the Edinburgh College of Art since 2019. She completed her architectural studies at the Technical University of Munich in 2010 and earned a PhD in architectural robotics from Hafen City University, Hamburg in 2015. She also studied at the University of Bath and finished the PG research-led program Open Thesis Fabrication at the IAC Barcelona. Cristina's work combines architecture, robotic fabrication, craft, and artificial intelligence, with a current focus on advanced robotic manufacturing techniques, particularly in clay and concrete. She investigates hybrid material systems and uses both digital and non-digital fabrication methods to create non-standard geometries. One of her major projects, Mini Builders, housed at IAC, uses a series of mini robots and has received international news attention. Her research and student projects have been presented at a series of major events, including ECC Architecture Biennale in Venice, Dutch Design Week, Frankfurter Messe, National Museum Scotland, EcoBuild London, and Festival of Architecture in Montpellier in 2019. Notably, her team received the People's Choice Award for their parametric installation, Le Papillon, if I spelled it correctly. That was a bit of French at the end. Okay, thank you so much. Without any further ado, we welcome Professor Cristina Nan. So the floor is yours. Thank you.
Thank you very much, Sina, for the lovely introduction, and very happy to share my lecture with you and your students. I'm going to share now my screen. Let's see. Perfect. I hope you can all see it. All right. So Sina, just remind me, how long should the lecture be? Because I love talking.
So like 45 minutes is good.
45 minutes. Okay, no, then we're good. I'm just going to update my timer. Perfect. So thank you so much for the invitation. So today I'm going to talk about my own practice and different research lines that I'm undertaking at TU Eindhoven. So it's going to be, I titled it Computational Tectonics. We're going to look at digital materiality, different robotic fabrication processes, and then synthetic spatial explorations through the use of AI. This is an overview of the different projects that I'm going to talk today to you. And I'm going to start off with a quote, which you probably heard, not for the first time. Technology is the answer, but what was the question, by Cedric Price. And with regards to the answer, there's two answers for me with the why, and quite on purpose, I'm going to start with space and humans. So for me, also having a background as an architect, it's quite important to look at not only at the technocratic aspects of digital fabrication or robotic fabrication, but to really start with the idea of the spatial exploration. And this is a quote by Zaha Hadid that I like quite a lot, where it's about architecture being more than about well-being. I think that people want to feel good in a space. On the one hand, it's about shelter, but it's also about pleasure. And the way I understand pleasure is a pleasure that is looking at new material expressions that come via digital materiality and robotic fabrication, and spatial qualities that can be enhanced through the robotic use, tectonic qualities also, and foremost, really an elevated spatial experience for the user. We all know when it comes to architecture and when it comes to space, of course, there are different styles, there are different expressions, but we all agree what successful spatial experiences or a spatial experience that touches us and elevates us. Here, for instance, so before we saw the Pantheon in Rome, here the Sagrada Familia in Barcelona, parametric predecessor, if you will. Here, for instance, Pierluigi Nervi's Oviedo aircraft hangar. And here to end the series with an impression of Zaha Hadid's International Airport in Beijing. The second part, to answer the question, why technology, is to also address challenges in today's construction. As we all are very aware of the fact that there is a resource scarcity, we are facing a climate crisis and climate emergency. There are non-sustainable building practices that are dominant, at least in, let's say, when it comes to Western building practices, very problematic material sourcing and high embodied energy or carbon footprints in construction. You all might know this statistic. Nonetheless, I think it's quite important to remind ourselves of it, that the buildings and construction sector, they accounted for 36% of final energy use and 39% of energy and process-related carbon dioxide emissions in 2019. I'm guessing 11% of which resulted from manufacturing building materials and products such as steel, cement, and glass, which is highly problematic. So we're trying to address with our students and with our research, we are trying to address these two dimensions of the problem, the spatial qualities and then sustainability, if you will, as a bigger umbrella. And what is quite important to me to mention when it comes to computational design and digital fabrication, it's not about the non-standard geometries per se. It's not about just going for geometric complexity for no good reason or for that to be really glorified. But what is most important for me is the shift that we are witnessing in the production conditions of architecture. And there's a shift also towards low tech, but at the same time, a shift towards high tech. So if you're envisioning a modern construction site, this is how it looks like. It's quite labor intense. It's quite massive. There's a lot of waste, material waste, and a lot of manual labor involved. If we're looking at well-known images of the car industry, of a car factory, assembly line, for instance, you can see the KUKA robots, industrial robot arms. It's all hyper-optimized, super efficiency, and very safe, also labor conditions within the factory. The shift in terms of the production conditions of architecture, the democratization of technology that happened in the last 30 years. You don't have to be anymore a specialist in robotics or studied mechanical engineering, AI, or a super proficient coder in order to be able to hack machines, to use microprocessors, to write your own software, to use desktop tools of fabrication or AR, VR, or even to control industrial robot arms. And the most from this whole shift in production, the thing that I feel is really opening up an entire palette of new possibilities also with regards to the job profile of the architect is the industrial robot arm, because it is a non-specific fabrication tool. You can use it you can use as an end effector, a spraying can, you can use a lipstick, you can use a saw, you can use an extrusion system for it, which opens up this really wide palette of possibilities. And because we have the democratization of technology and the availability at our fingertips of all of these machines, for me, the focus is really set on rethinking and redesigning process, because at the end of the day, the machine is a tool for fabrication. And you can really rethink, recurate the way you're working with concrete, the way you're working with clay, keeping in mind, of course, all sorts of parameters and constraints. And this is also why I'm going to touch slightly on the aspect of craftsmanship, because the moment you are mastering a tool, any given tool, right, we're already in the realm of craftsmanship. What does that mean in terms of the understanding that you have to show and demonstrate with regards to the tool itself, the constraints that come with the tool, the relationship between tool and material, geometry, etc. So for us, it's very important to have an integrated system thinking. On purpose, I didn't put geometry or form as a first starting point, where we see this as this continuous loop between parameters and constraints regarding material, machine, geometry, fabrication, assembly, structure, where computation and computational tools form the red line, or in this case, well, the blue line. Right, so if I change any of these parameters, it will have an impact of the whole system thinking that needs to happen. If I want to print something out of concrete, and then change my mind that maybe it should be out of clay, it's quite likely that you will have to redesign the entire process, and not only of making, but also in terms of geometric considerations. Now, this is very faded. I'm not sure if you can see the different colors. So at the center of our thinking, we're really focusing on how do these tools change the design thinking, and that we don't start necessarily from the form or the geometry itself. How do you redefine process, and what does digital materiality mean, and what type of new expressions can be imposed on the material? We're looking at analysis, simulation, and evaluation, and feedback loops, different types of material systems. Of course, a very strong focus on a sustainable material use and the reduction of waste, circular approaches, and then additive manufacturing, and of course, computational design. And this all is at the intersection or at the threshold between architecture, engineering, computation, and AI. One more, because process is really important to me, and to really emphasize the fact that we are not starting from geometric considerations at the very start, and that the processes we curate there are open-ended. We don't necessarily know what is coming out of it, and we don't particularly care as long as we understand, as long as we even learn from failures in setting up the process, and we have an original design thinking behind curating the processes of making and design. And another thing that I'm just slightly going to touch on now, in the wake of AI and the extreme robotization of different fields, there's a lot of conversation with regards to labor, right? So what does labor mean, not only in architecture and engineering, but you will have read probably a lot of headlines where it's like, oh, architects, engineers, I don't know, lawyers are going to become obsolete because of AI, robots, automation. What is quite important, and with one of the projects that is focusing on discreteness, I'm going to touch slightly on is that I don't see the use of the robot as an absolute given, right? So sometimes you might be able to use a robot to assemble a structure, but does it really make sense? And where's that threshold where you consider, okay, yes, I could do that with the robot. I might have a 10% increase of efficiency, but considering sustainability also with regards to human labor, it might make more sense to actually let humans assemble it. And this is quite a nice quote from David Benjamin. I see that it's covered at the bottom, where he's saying, well, architects organize materials, but also forms of labor, whether we perceive our drawings and specifications that way or not. And this double embodiment should be inseparable when we make our calculations of expenditure. It should also remind us that sustainability has to be framed in social as well as environmental terms. And now, so this was the overall introduction of the framework under which we at TU Eindhoven, but also particularly myself, are operating. Now I'm going to show you a series of research projects that are my own or undertaken at TU Eindhoven, touching on different aspects that I have just described. This is the installation of the Papillon d'Or. I'm just going to see and try to, yes, perfect. Okay. This is the installation of the Papillon d'Or. I collaborated with two friends of mine, Carlos and Dirce, from back then, Zaha Hadid Architects and Heatherwick Studio, on this installation. It was within a courtyard of a music school in Montpellier. And yeah. Right. It's based on a minimal surface. Also, as usual with competitions, there was a really limited budget, and we were based in the UK and had to make our way with the installation from the UK to southern France. This is how we first tested the minimal surface at the scale of 1 to 5 at Edinburgh University. Here we used, so the whole structure is here made out of 7 A1 sheets of really normal paper, and just fixed together with tiny paper clips, trying to test the geometry and if gravity would really hold it in place as we expected. This worked. Then we're on our way to Montpellier, where of course, again, transport was an issue. The way we thought of the structure, because we needed to fill up the entire courtyard with this type of structure. No, you have children. We didn't really want them to pull or tear at the structure, yet we wanted to offer them a particular type of spatial experience. So what we did there, we have the whole subdivision strategy of the installation, and all of the parts and pieces for the entire installation, 8 by 8 by 7 meters. So fitting within that type of volume. You can see here in the background, so this were the maps where everything was fitting into, and we had a total weight of the whole installation made out of PETG, so recycled plastic, basically from your water bottles, and golden vinyl fitting within the requirements of 20 kilograms per suitcase. Here you can see the hanging structure in the courtyard. And what was quite nice, and again, in terms of the spatial experience, since we didn't want the children to directly touch the installation, as we couldn't be there on site 24/7, we thought, well, let them interact. Then with what else could they interact? And we're thinking of shadows. So this is the type of shadows that it would throw within the courtyards, within the courtyard. And to our surprise, the children really loved running through the shadows, trying to catch them, playing with the reflection or interacting with the reflection of the Papillon d'Or. So we found that it was a quite successful installation and exercise. I'm working multi-material across different material systems. One of them is concrete. If we think of concrete, right, and the material expression that comes from concrete, this is the normal the normal surface texture we would encounter, right, from the that is really defined by the casting and fabrication process. What we were testing back then also at Edinburgh University was how can we impose a different type of material expression and ornamental value on the concrete in a very simple manner. We were looking at fabric formwork. So one of our MSc students from Material Practice, a program that back then was run by Professor Remo Pedreschi, he developed his own silicon printer. So we started making trials with a silicon on textile. Here you can see the fabric formwork. At first it looks quite as a dirty process. This is the amount of formwork, textile formwork, that is needed for the casting, and we were printing on the inside of the material with silicon. Silicon has the nice property that you could destrap the whole column. So here's one of the first tests. The silicon would remain intact, and you can even reuse the formwork by just restitching and closing up the ends. Here's another experiment that was undertaken following the same type of process, where you can see here now the type of imprint that you would have from the silicon on the concrete surface. Also, with regards to sustainability and circularity, if you would have wanted to print another pattern, you could remove very simply, so the silicon would peel off, or very simply from the fabric, print another pattern on it, and reuse it again for casting. So this is one way of imposing an ornamental expression on the concrete. Since I'm at TU Eindhoven, I'm particularly focusing on 3D concrete printing, where in most of the projects I'm collaborating with the company Vertical, also based in Eindhoven. For me, it's very important that also my students, we're not only running, let's say, dry experiments or small scale experiments with regards to this technology. So here you can see a picture from a seminar where the students within 8 weeks had to develop proposals for full scale 3D concrete printed columns, but also to give them the experience of what does it mean to prepare a G-code for the scale 1:1? What type of considerations do you have to take into account when it comes to extrusion rate and speed, etc., when manipulating the robot? These are some of the 1:1 scale columns that were printed, where different type of patterning strategies were tried for the surfaces, right? So here you can see also some close-ups. Then for the campus, we were looking at urban furniture, which was part of a second seminar, also in collaboration with Vertical, where via the means of computational design, students developed here this type of parametric bench for on campus. Concrete, it's very durable. What we also observed, people love to sit on it and to really touch and interact with the texture of the surface, but also it was quite stable due to the ripple effect that we built in. Also 1.5 tons of weight, so no chance that the wind would move it away, or that there was any type of danger of the structure collapsing. Then, with regards to 3D concrete printing, this is a recent research project that was a collaboration again with Vertical and with an architecture practice, Neutelings Friedijk architects from Rotterdam, where we were looking at filigree systems for facades and how these can be printed without using molds, as the largest cost associated with the production of concrete structures and components is related nowadays to formwork. In order to do this, we were looking at sand as a recyclable formwork, where we can impose different types of geometries on top of the sand. What we started doing first was we tried out different types of end effectors to achieve this type of lenticular geometries. And here you can see some simulations of the robot arm with the different types of end effectors for moving the sand, trying also to understand how much humidity we need to apply. Do we need to apply any type of coating on top of the sand? The answer is no. At some point we were applying water, so just simply spraying water on it for the sand to set a tiny bit more. But what we recognized was that even without the step, that particular step, you would have the same type of surface resolution with regards to the sand surface or the sand mold that you would create. For the facade system that we were investigating based on a filigree system, we arrived at the conclusion that we are going to use lenticular, lenses with regards to the sand formwork. This was one of the first end effectors, where we were trying really just via circular movements to shape and define the sand. This is the type of movement that we followed. Of course, you saw that end effector, right? The blade was far too long to achieve a high resolution sand formwork. We modified that, shortening the length of the blade on top of the wooden end effector. Here you can see some first experiments with that type of, let's call it spatula, moving and shaping the sand, and this was then the final resolution that was used for printing on top of it. We used the non-uniform growth algorithms to experiment with regards to the geometry that were multi-layered from 1 layer to up to 5 layers, where here we can see the robotic setup, right? So the robot was moving on the tracks, where we were looking at how we can calibrate the speed of the robot on the tracks with the extrusion speed, with the flow also, in order to also have a staggered printing, aiming basically to use less material. So as you go higher with the printing, that you have a material depositing strategy that also reduces the thickness of the 3D printed extrusion line, according to a simulation where you would only need it. Here you can see this should, no? It's not, okay. This should have been a video. So here you can see the printing of the different layers and how they start to be staggered, but this should be a video. Let's see. Yes, right. So here you can see the printing. Overall, to form, the process was very efficient. To form the sand per sand lens, it would take you something like 12 minutes just to form the sand, because of the repetitive, right? You had to achieve a fine resolution of the mold. You had to go several times over the sand surface. To then 5 to 7 minutes printing time of the entire lens. We were also looking at what is the more efficient material depositing strategy. Should we go at a 90-degree angle towards the construction plane, or aiming at 90 degrees angle on the shape of the sand itself? The answer is the second option was the better one, as it wouldn't, the robot wouldn't deform the extruded layers on top of the sand, and you would have a better layer adhesion of the concrete on the sand, other than just printing vertically at 90 degrees. These are some of the final prototypes that we produced. As you can see, they're relatively lightweight, so they're all somewhere in the range between, depending on the amount of layers, between 15 to 20 kilograms. And here you can see also the shadow effect if they were to be part of a facade. Right, ones with frame, without a frame, different types of openings. And here you can see some visuals as part of an design proposal that was coming from Neutelinx Redux architects, and currently we are investigating ways in which we can move this research forward and actually build a whole one-to-one scale sample of the entire facade, with also the supporting elements also to be 3D concrete printed. Another area of research and material system I'm currently working with is clay, in the future also earth printing. Why earth and clay? So when we are thinking of modern construction materials, normally we're thinking of steel, we're thinking of concrete, we're thinking of glass, but earth and clay are materials that are nearly everywhere available. And here you can see a map of the world with the different earth construction areas of the world. So these are areas where earth construction is or used to be the norm in terms of the mainly used building material, which then through industrialization was replaced with steel, glass, and concrete. And we might generally not be really aware of it, but it is estimated that at least 30% of the world's population live in houses constructed of raw earth. And what is very compelling about earth construction, rammed earth construction, it's an incredibly simple and easy construction method that can be also taught to non-initiated people. Mud and earth can be used entirely untreated. It can be nearly endlessly reused, and it's a local material with a global availability. And other than ceramics or ceramic 3D printing, it does not require firing at all, which also reduces the embodied energy. When we're thinking of clay, I mean, there is now this whole trend within the discipline of 3D clay printing, but of course it has also predecessors, and there's a rich history of the use of ceramics in architecture. If we're thinking here particularly of facades, the Portuguese tiles, where they are indeed used as a highly ornamental part or component of the building. This you might know, this building from New York by Louis Sullivan, where it's a steel construction which is clad with this type of red terracotta tiles in its entirely over the whole facade. To then write a more also from the US, a more recent example, the Center for Asian Art, by Silvetti Architects, where also clay or clay components, clay tiles are used as a facade and cladding system. The lines of investigation that we're focusing on, or the different points that we are trying to explore right now with clay for us, are the ornament and the ornamental within architecture, and what that could mean. I'm trying to avoid the word style, but what that might mean as a new form of expression within architectural discourse today. Spatial transformation of the building itself and for users. We're looking particularly at custom architectural cladding components, digital materiality, so the type of material expression that can be imposed via the robot and computational design on this type of material systems. And what becomes very, very relevant is subdivision strategies and also assembly strategies for this type of cladding systems. And for a current research grant that we're applying in collaboration with behavioral psychologists, we are trying to see and quantify also the impact on behavior and cognitive development of this type of materialities on the human user. Now, when it comes to, I'm not sure if you ever worked with the ceramic 3D printing, there are some challenges to it. Of course, concrete comes with its own challenges, but let's put it this way: ceramics has, or clay has a bigger temperament than concrete. One of the issues is material consistency and moisture content. It depends a lot also on the season. So we have our recipes for the clay, and normally we use clay with 5% chamois, which is sort of sand, and just mix with water, no other type of additives. Yet if you're printing in summertime with the same recipe versus printing in wintertime, it is highly susceptible to the room temperature. So you might have issues with clogging and the extrusion, as it will dehydrate a lot faster in summertime. Then material flow, drying and cracking, also shrinkage. Clay, particularly when you 3D print with it, it's subject to non-uniform shrinkage, meaning it will shrink in different rates in X, Y, and Z direction, highly dependent on the geometry. Also, cracking can appear, not necessarily because of too fast drying, but because of the tensions within the material caused by the geometry itself. Plastic deformation and collapse during the printing itself, right? So there also we adapt, sometimes manually, sometimes within the code itself, the printing speed, right? So we reduce the printing speed when we get past a certain height in order to give the clay a tiny bit more time to dry to a certain extent so that the whole structure can become more stable. We're always printing without support structures so that no plastic deformation occurs or no collapse occurs. Warping is also a big issue when you're, so it can and it will shrink in a non-uniform manner, which is very problematic when you have a tiling system or a tessellation that is going on, but also it can warp, so it can distort the geometry, particularly also during the firing. Because, well, clay has to be, or ceramic components, they have to be fired twice. Normally we do bisque firing at 800 something degrees, and then a second round of firing at 1040 degrees. And also there, during firing, warping can occur and cracking. So this is the type. These are the type of machines that we're using. We're using the WASP Delta printers, 4100, with an external feeding system, meaning that you can always throw in new material during the printing, and you're never constrained by the capacity of the container itself. We're also doing a lot of test prints. Trying out different pigments within the mixture itself in order to avoid the second round of firing that is required for the glazing. As said, so for instance, for this type of components that were exhibited 2 years ago at the Dutch Design Week, we were printing them without any type of substructure or support structure, and there you do risk you have a highly increased risk of collapse and plastic deformation. As you go past this point, the different arms are not touching one another, so they're embedded within the code, or manually you have to substantially reduce the flow of material and the extrusion speed in order to avoid the collapse of the geometry. And here's some other impressions from that. With our students, we're also doing a lot of tests with regards to facade systems. So here you can see some proposals from them where, as I mentioned, the tessellation and subdivision strategies, where really the joints are becoming super, super important with clay, and how do things how will things lock in with one another. Here you can see also when collapse is happening and plastic deformation, how that looks like. So this was a facade panel from that paragraphic that we were showing, and as we were getting to a certain point, the speed wasn't reduced sufficiently, and you had plastic deformation then leading to collapse of the component. Students of mine that just recently graduated, they were looking also at different types of patterns. Here we have the Turing pattern, which is represented in nature. You will know it from corals, from brain growth, etc., and trying to impose it on the clay tiles. Here you can see, and you're going to see in a second, the final results. So here you can see the fired clay tiles. We're also looking at post-production techniques, also a tiny bit at sanding, and particularly at glazing. This is then, so we're using different types of, we're experimenting with a lot of different types of glazing mixes. This is then how the glazed finalized product looks like. Where you can see here, for instance, so whereas other pieces are perfectly aligned, here some of them during firing were prone to warping and distorting slightly the geometry, leading to this type of gaps. This is another student project, also ceramic facade systems. This is then the final output. As mentioned, glazing and color is quite important, as it does give this finishing touches here with molten glazing. So it's a runny type of glazing that will, as it's fired in a horizontal position, it will really melt in some sense of the ceramic and will create this type of colored pools that then are reflecting the light and really amplifying the impression of depth on the components. Another project where that was just finalized with our postgraduate students, computational clay columns, where we were looking at the value of dissecting the column and cladding the column. This type of research has been undertaken, for instance, also at the CETA Institute. We followed a different approach where we were really looking at the infill and trying to expose the infill that is normally hidden. But first of all, so with regards to the material expression on the level of the skin, we were looking at sine waves and at water ripple formations, trying to quantify them and experimenting here with different, so here you can see, right, different type of segments of the column cladding, trying to quantify really the speed flow, amplitude, frequency, but also the layer thickness and the type of shrinkage that we were encountering. Quantifying the drying shrinkage is quite tricky, again, because it's non-uniform and it highly depends on the geometry, trying to use different formulas and embedding them in the code. So you always have this process loop. You're trying out something, you're printing it, you have to measure the shrinkage, put it back into the system to make sure it's embedded, so that once you're printing it and then assembling the whole structure, you don't have significant gaps and that things align. Also, different type of layer extrusion strategies that are informed by the patterning. So the pattern isn't just imposed on the surface structure in, let's say, in a dumb way via graph mapper. Right. Then these were different types of geometric investigations for the columns, whereas you can see you have a structural core that also can be activated for different type of functions, such as airflow, airflow and air circulation, heating, for instance, which is there to stabilize the whole column and then the actual cladding around it. So we followed an approach, and our students followed an approach where we really wanted to give also an aesthetic value to dissecting the column and showing what is happening inside with regards to the needed infill and the tubular structure. So there you can see on the left-hand side at the top, the infill structure for the column and the cladding. And here you can see the exploded column section, where also we're doing all of these pieces are printed simultaneously at the same time. It has something to do with, if you're printing at the same time, they will lean, they will lean in some sense against one another, and it will diminish the warping and the torsion that they experience. But it also, you are making sure that you have the more uniform shrinkage than if you were to print them separately, and that they are also all aligned, that you can assemble and disassemble them. Here are the different components of one section. Currently this month we are going to print one of the columns at full scale, at scale 1 to 10. Sorry, full scale would be a bit much. And here you can see also the quantified shrinkage. So the shrinkage you're dealing with is quite significant. So if we're looking here at this sample, one is the wet state, the dried state, and then after firing. So the shrinkage that you have to account for is quite dramatic, whereas so this is here within the body, whereas here at the tip you have a different type of shrinkage rate. So all of this has to come back into the code. There you can see the step-by-step printing and the detailed sections of the print. Also with our printers, we can do stop and go. And what I forgot to mention is the column cladding and the inner infill and the support, they are being printed at different heights. And this has something to do with then the cumulative interlocking strategy for the whole structure. This is, so what we're currently printing right now. There you can see a close-up where you have the skin, the inner cladding support system, and then the inner tubes that are stabilizing the whole structure. In 1 to 10, we are going to have for an entire column, which is human size, because also side note, these were designed for the Caracalla bath in Rome. We are going to have 50 different components that need to be assembled. The nice part here also about the clay, so whereas one of the concrete columns that I showed before had a weight of between, depending on the geometry, 300 to 500 kilograms, here you're dealing probably in total with 30 kilograms for a column of the same height that is structurally stable, and where you don't need cranes, trucks, or anything to transport it. It can be put up in boxes and then assembled out of the 50 pieces. And this is within the Caracalla bath in Rome, right? The position of the different columns that we were looking at with our students. And these are some visuals for the full-scale structures as suggested or well, speculatively designed for the Caracalla bath. Right. Also with regards to, I'm just looking at, right. Also with regards to clay, and here I'm going to go a tiny bit faster through this part. We were looking at another site in Rome. This is part of the Forum Romanum, the Maxentius Basilica, where basically, well, this is on the left-hand side, you see the basilica as it used to be. On the right-hand side, the remaining ruins, and the students were tasked to redesign one of those lost walls that we don't have anymore. We were looking at structural analysis of the vault, at the force flow lines and the stress lines, doing also topology analysis, which is not part of this presentation, and then trying to, well, to order the force flow lines, defining the different regions amongst them, and then in between there where less material structurally was needed to create this type of porosity strategy for light to go through. You can see again the perforation strategy and how it goes hand in hand with the force flow lines. Also giving different thicknesses to the components as needed within the overall vault structure. Here the different force flow, the different computational processes regarding this. Then the segmentation strategy, where we really went for a very rigid grid that was imposed on top of it, as we are planning to print all of the components flat in, well, also, I believe this one is planned to be printed at scale also 1 to 10 in order to make it manageable also for stacking and for transport. Here you can see an impression of the overall vault if it were to be put in place with, well, the also a porosity strategy and the type of light effect that it would create for the visitors with shadows. Jumping to an entirely different approach and project. 2 years ago, we organized at the university the conference Robots That Build. It was a conference going hand in hand together with an exhibition on robotic fabrication, which was with robotic fabrication. That was looking particularly at robots, new materials, circular material systems, and craft. For the curation of the exhibition, so 300 square meters, very limited budget, very limited manpower. You had to assemble it because it's the main hall of the building. You have to assemble it very quickly and easy, and non-specialist labor, meaning we were using our students. For the whole exhibition. So what we wanted to avoid waste entirely, to have a circular approach, low cost, that we could extend it if needed, as we didn't know what exhibit exactly, if all exhibits are to come in and at what time. It should be lightweight, well, because students should be able to lift the different components, form a spatial agglomeration, and be volumetric. So in order to satisfy all of these requirements, we went for scaffolding, and we felt that the discrete design logic is the best way to go. In case you're not familiar with discreteness, discreteness, it focuses on the development of architectural objects as reversible assemblies of generic parts, right? And this is why we found, exactly because a scaffolding is a reversible assembly of generic parts. This is why we went for a scaffolding system. What is quite interesting also about discreteness, it's a whole trend within today's larger computational design discourse. It's also being often used as an argument to redefine, or is it process or way of thinking to redefine the entire production chain of architecture. And it asserts that a digital form of assembly based on parts that are as accessible and versatile as digital data offers the greatest promise for a complex yet scalable and open-ended and distributed architecture. So these are some examples of discrete architecture by Gilles Redsin. And what we used, so we defined our material system, which was the scaffolding, the discrete design logic, and we used the Grasshopper plugin WASP for it, right? Which is different from WASP, the 3D printers. This was the zoning strategy and the different materials within the hall. And here we have the 300 square meters. What we did is we wanted to have this different zones within the exhibition, as mentioned before in the floor plan, grouped according to, robotic technique and used material, but also because it's the main hall, to have some very clearly defined circulation corridors and exclusion zones for the structure. This is the type of discrete agglomeration that we generated, and in order to do that, we followed the following logic. So we worked with what we called towers. We had vertical parts, which were these assemblies that were, we had the bottom that had to be under each tower, and then we were working with different heights, and these are just the towers volumetrically represented, but actually it's this type of scaffolding within it. And then with a footprint of 50 by 50 and another footprint of 75 by 75, we needed horizontal scaffolding beams to stabilize the whole structure. And in order to have this volumetric impression, to also have horizontal hanging boxes that would come out from the towers and meet another tower. What was quite, so we used WASP for the entire process. What was quite nice is, so because scaffolding is a standardized product, it was very easy to put this within WASP, within the system, to define how many parts you needed to build. So you weren't relying on having first a robot that needs to fabricate the things, but by obviously using scaffolding, that is a pre-existing system, you're bypassing entirely that step. And then we added by hand this amount of items from each component, where we felt that just to be sure that the structure is safe and stable because of the weight of certain exhibits and because of the circulation flow. Here you can see the strategic positioning in the entrance hall of the different components. We never really had an assembly strategy or sequence. Well, we did have an assembly sequence, but no one used to really needed plans or drawings to understand how the assembly went, because it was really intuitive as a reference point. The pillars were always used, and we just had to look at the 3D model to basically count the amount of bases that you have to place, and the structure would go on its own. So here you can see the assembly sequence. So you would start with the placing of the large exhibits, prefabricating the towers, placing the towers very easily manually, then the horizontal slabs, which were really where things would fall into place, and you would know that the position is really locked in, of course, because of the grid that we were following. And then finally, by one of my colleagues, the structural testing, just making sure that, well, everything is latching onto one another the way it should. And these are some impressions from the exhibition itself, walking through, and the way that we use the scaffolding. Needless to say, we nearly had zero waste. The only waste were the orange panels that where we had, right, the photographic documentation printed on it. So with regards to zero waste exhibition, we think we were very successful, almost getting there. I think I'm slightly over time, but still I'm going to go quite quickly through this last project where we're looking at AI, and we're just calling it right now architectural hallucinations as a bigger investigative line. So when we have artificial intelligence in the architecture, engineering, and construction sector, there's all different application areas. The ones we are currently focusing on within our research group, so there's others research groups at TUI that of course are looking at analysis, optimization, evaluation, real-time tracking, etc. But we are looking at it from a critical point of view. How can it be part of the creative input in a meaningful manner as a design tool for geometric complexity, and to really offer particular or not sufficiently explored spatial experiences. And also looking then with regards to the bigger picture debates at questions like authorship, control, creativity, and what is the creative genius. I believe at this point we all know about Midjourney. What is also quite interesting about Midjourney is how it describes itself. It describes itself not as a social media platform or something like, I don't know, Acrobat or the Creative Cloud, but as a new type of research lab aiming to expand the imaginative powers of the human species, right? How we write a prompt, imagine, yes, and these are the type of prompts when you're typing, I don't know, urban architecture, computational, algorithmic, whatever, not, these are the type of outputs that you get that are not necessarily useful, or the question appears, and where do we go from here? We were trying to map the phases of design with regards to, well, we're starting from inspiration. You have a sketch, maybe model making, and then some sort of graphic representation, plans, drawings, 3D models, and it's all this progression from the imagined and the fuzzy, the diffuse, the ambiguous, to the then very concrete, clear, controlled, and ambiguous. For instance, here, Bilbao, Frank Gehry, trying to understand how does that process really look when we're using Midjourney, but particular neural networks, what we were focusing on, and style guns. So trying to understand how data collection and curation works, and with the focus on how do you translate, once you have a synthetic image, and once you determined how you're collecting your data and how you're curating also the input for the style guns, how do you then translate the synthetic image into something meaningful? So we first used style guns to do this type of explorative materiality studies to see, okay, what can happen when we're really exploring different material expressions for reclaimed materials. Then just just in terms of, I'm sure you all know this, but just if someone has an unclarity in which field we're moving right now. So I'm referring to what we're doing is anchored within machine learning and neural networks, and well, general definition of machine learning. It's the study of computer algorithms that allow computer programs to automatically improve through experience. We're using our own neural networks or style gun, which are generative adversarial networks, which are all there are function approximation algorithms. I'm not going to go into a lot of further detail into how the style gun is set up, but so we started first with very small data sets where we're trying to look at different types of or new types of material expressions that can be imposed on Earth or earthen architecture. So students have to collect their data, make up their data sets. Then there's a whole logic of the data curation, the training of the guns, then the different seed generations. We were working on this together with a researcher, Dong-Yoon Kim from Harvard University, trying, so I'm just going to go because I'm very aware of time, going in a bit bigger jumps throughout this whole process, but just for you to understand the logic of thinking behind it. Where we were really jumping. So what we also use for the style guns, and when you see here Midjourney, so we inputted also, because for some of the databases, using information available online wasn't quite enough to push it to a particular type of material expression. We're then generating images via Midjourney in a strategic manner and integrating them into the data sets of the style guns to swing the output into a certain direction. All sorts of self-imposed parameters of assessment for this type of earthen architectures. Then also using Rhino Grasshopper to go through different processes of rationalizing the geometries, imposing structural systems on them, and testing how this type of unlikely geometries could be built, going through different types of building sequences, students translating them into architectural drawings, testing also the printing. So there you can see the print was successful, or the operation was successful, the patient was dead. It then, well, collapsed under self-weight at a certain point when we tried to move it. So it's this whole curated, well, process between style guns, Grasshopper, Rhino, sketching, conventional designing, optimizing, testing, and printing with clay. This is another student also with a focus on earthen architectures, trying to develop a thinking with regards to how could that type of rationalized architecture be built, and then arriving to this type of, well, final result, which is substantially different. So as a last thought, what is important to us is it's never the aim to achieve that the particular expression of the synthetic image, but it's rather as a starting point for a playful experimental line of process and investigation regarding form and geometry and the making of it. And finally, because I'm always scared that with all of our discourses and robots, algorithms, we're drifting into the field of techno-fetishism, a quote that yeah, it's very important to me since I heard it during my studies ancient times ago, that, well, pencil and computer are just, if they're left to their own devices, equally dumb and only as good as the person driving them. So irregardless of these tools, they can be used in a circular, sustainable, and meaningful manner only if you really have concrete strategy behind it. You understand material, the tool, and you develop your own line of design thinking, aiming towards a larger goal and not per se a specific geometric expression. Thank you very much. And I hope.
Thank you very much, Cristina. So we don't have that much time left, unfortunately, because like most of the people attending have to attend other classes. So we have like maybe like a couple of minutes for some questions and answers and reflections. Anyone has some idea or question? Want to? Yeah, we have one. I think if you talk, let me change the microphone.
Is it cost efficient for building facades and using it for, future projects?
If the clay or the concrete?
I guess a little bit of both, maybe.
Well, yes, it depends how you measure cost efficiency. So with regards to material use with robotic fabrication, you can really minimize the waste. So already for talk in terms of costs and the material that is coming in, yes, it is more cost efficient. Also not with mass customization. So other than producing molds that have to be, well, it's either the same mold for everything, or the moment you start to build separate molds for each component, it becomes extraordinarily cost intensive. So overall, if you're after complex geometries and or non-standard geometries, yes, it is more cost efficient than traditional production approaches.
If you want to ask.
Sure, yeah. I was gonna ask if Grasshopper is still the primary software for this sort of construction, or if it seems like the industry is heading in a new direction.
For us, it's really Grasshopper, but it depends. So I think for everyone it's still Grasshopper, but of course within Rhino now you have also BIM embedded, right? You have also Speckle. You have a lot of different platforms that optimize the information flows. But I think what is really exciting about this and why Grasshopper I think is here to stay, you can bypass all of those things. And if you have access, or if you can rent a robot, it's just you and your G code and inputting it to the robot, and you're in control directly. So it's file to factory production, and there's no middleman in between, which a lot of practices so they're quite tiny, or they're startups like La Máquina in Barcelona or Studio Rap in Rotterdam. They're following exactly that approach. So I think, yes, I think for now or the foreseeable future, it is going to be Rhino Grasshopper for this type of approach, at least.
Maybe a follow-up to what I had asked and your answer, like the last project that you showed and how you were trying to use like generative AI, whether through the lens of Midjourney or kind of a trained data set. What was interesting was to see how architects can customize their workflow and then develop a customized workflow for benefiting from something which is accessible to everyone, but like really tailor-made it towards what we need and what we can benefit from. So I think that was a good example, because like obviously like in our design process, we use a lot recently to imagine or hallucinate, the way you were saying. But then how we turn that hallucination into design is also interesting.
Yes, yes, that was really for us the question, because you do have all of those seductive images on Instagram and LinkedIn posts and whatever not, and you're like, yeah, okay, it's a nice image, but architect, right, how do I build it? How's the detail, and how does it bring me in any way further? And particularly students, they're quite blocked. They don't know where to go to next from it. So trying to curate with them this type of workflows of, okay, that thing is a tool, and that's really your default position, And it's not about a one-to-one impression of that, in some sense, really dumb image, because, well, you don't know what is happening within the black box of your style gun, even if it's self-scripted or of Midjourney, and you get something out where then, well, it's the death of creativity in some sense, if the ambition were just to be that image. And seeing also how far you depart from that the moment you have to rationalize it and think of, well, structure, analysis, and material and fabrication strategy.
Unfortunately, we have to close the session. I see that some messages are also sent online. I will try to collect these and then maybe later send it to Cristina.
Sure.
Yeah, so we have to close. And thank you so much again. It was fantastic, informative, and a lot of energy. Thank you.
Thank you very much, everyone. I hope you all enjoyed it, and wishing you a productive rest of the day.
Thank you. Thank you. Bye-bye.
Bye-bye.